So far we have been pretending like we know how to measure X-rays, but I haven't really given you a full picture of how X-rays are being measured. We have dealt with the fact that we do collimation, but how do we actually get an X-ray into a measured signal? And this is what I want to discuss in this section. So we have, after collimation, we have the detection that consists of a scintillation crystal. So a typical example here is thallium-doped sodium iodide. We have the X-ray that hits this crystal, interacts with the crystal. What happens then is visible light is being produced. This light then impacts on a photomultiplier tube, which basically produces a lot of electrons. They're multiplied, and this in the end produces an electrical signal. So this is schematically, we have X-ray interacting with the crystal, conversion to visible light. This visible light is amplified into an electrical signal using a photomultiplier tube. So here's the complete process. Here we have the source, we have the collimator, crystal and scintillators, and then we have the photomultiplier tubes that produce the signal. One important feature of this detection process is that the energy of the gamma photon, of the X-ray, 140 kiloelectron volts is one example. This energy is proportional to the number of scintillation photons. Those are these guys here in white. And this, in the end, is proportional to the signal that we measure. So the intensity of the signal that we measure is a measure of the energy of the X-ray. And this is important as an important feature for the emission computed tomography techniques that we're discussing this week and next week. So what is scintillation? What happens in this scintillation crystal? So there are a sequence of events to consider. We'll have here the gamma ray, the X-ray that hits our crystal. It produces a primary fast electron. This can be an electron bumped out of an inner shell through the photoelectric effect, or it can be an outer shell electron that's removed from the atom by Compton scattering. This electron in the crystal will then produce a number of excited secondary electrons and actually electron hole pairs, which in the end produces the scintillation photons. So it makes perfect sense. If we have a higher energy X-ray that comes in, the energy, the kinetic energy of the liberated electron or electrons is higher, and therefore they are capable of producing more secondary electron hole pairs, and therefore they will produce more scintillation photons. Hence the proportionality of the visible light to the energy of the incident X-ray. So we'll consider here that the atom is ionized by a Compton interaction. This produces an electron hole pair. The hole ionizes the activator. The electron falls into the activator, and so when the activator is deactivated, it goes back to the ground state, it emits photons, and it does that fairly fast. Here the example is on the order of a tenth of a microsecond. If we look at it from an energetic standpoint, we have a gap in the solid state, we have the activator ground state, and we have the activation band. This band comes actually from the doping here. So this is GSO with the doping here indicated. So I won't go into the details and the physics of scintillation. It's fairly complex. It's not a strict, precise description of it. What suffices for us to know is that we need an impurity in the crystal, and that the number of scintillation photons that are produced are proportional to the energy of the incident X-ray. So now what we have is we have excitation, we have an energy transfer, and we have emission. But we have also quite some losses due to heat. And so we're interested in characterizing scintillation materials, and that's one thing is the efficiency of the scintillators. This is essentially the energy of the scintillation light. So energy of the visible photons times the number of photons divided by the energy deposited, typically the energy of the incident X-ray. And this is proportional to the energy transfer efficiency from the excited ion to the luminescence center. So how good are we in bringing that energy to the impurity? We have the quantum efficiency of the luminescence center. How efficient does it produce the light? And how much energy is required to generate an electron-hole pair? Again, what makes sense? If we need more energy to create a hole pair, the efficiency is lower. If we produce more photons from a luminescence center, the efficiency is better. And if we can get the energy transferred to the luminescence center very efficiently, then the efficiency goes up. So these relationships make sense. So instead of going through the theory, I wanted to share with you some scintillation materials here and the characteristic that typically are used to characterize them. So there's a whole bunch of different materials here. What we notice is they are fairly heavy materials. So the density ranges between 3.7 for sodium iodide to around 8 for this compound here. The attenuation coefficient, obviously, we'd like it to be high. So it's somewhere between 0.3 and 1 per centimeter. This is the attenuation coefficient at 511 kiloelectron volt. Then we have the light yield. So how many photons, scintillation photons, are being produced per kiloelectron volt of the incident X-ray? And we see here we're ranging between 70 and 40 photons per kiloelectron volt. So we have sodium iodide, which is among the most efficient here in terms of energy yield, produces 40 photons per kiloelectron volt. The wavelength of the scintillation light here ranges between 360 and 600 nanometers. Here's a time constant tau given in nanoseconds. This is the time it takes for the luminescence center to return back to the ground state after it has emitted a scintillation photon. This essentially gives you an idea of how fast is the scintillation crystal reset and ready to detect the next event. This is important because if we have a lot of photons that are being detected, we want a fairly fast crystal so we can measure fairly fast. If the crystal has not been reset back to its ground state, it cannot measure the next event, and so we lose that event from the measurement. Here's some ideas what are the effective Z of the materials, the refraction index, and the yield that we have. So what ideally would we have for requirements for a scintillator? We want to have a high yield. We want to have good linearity. Obviously, we'll discuss more why that is. We want a small time constant. Like I said, we want to be able to measure every event that impacts on the crystal as fast. So we don't want to miss out on a second event. And if we have two events that come fairly short after each other. Of course, it should be transparent for scintillation light. There's no point in producing scintillation light that is immediately being absorbed by the crystal. Not to forget, it's a physical process. We're producing a mechanical camera, so it should have good mechanical properties and a refraction index close to 1.5 so that the light is being reflected through the crystal and is being detected by the photomultiplier tubes. So let's look here at the light yield. And the thing that we have to bear in mind is if we have a photon that impacts our scintillation crystal, most of its energy is lost to the lattice in the form of heat. So I'll give you here just an example. Let's say we have a technetium, metastable technetium-99 scan. So the photons are at 140 kiloelectron volt. And we'll take the sodium iodide scintillator crystal. That's this material here. So we have a yield of 40 photons per kiloelectron volt. So if we have one of those X-rays impacting the crystal, we are producing 5,600 photons with a wavelength of about 400 nanometers. It's 415, but this is good enough for our estimation here. So we have 5,600 photons with a wavelength of 400 nanometers. Now the energy at 400 nanometers, we can calculate that from the equation we've introduced in week 2. So that's given by hc through lambda, so it's 1.2 divided by lambda. If we give lambda in nanometers, that's the energy in kiloelectron volt. So that's 1.2 kiloelectron volt divided by 400 nanometers. And so the visible light photons, they have a energy of 3 electron volts. So we are converting 140 kiloelectron volts into 5,600 photons of 3 electron volts each. So 3 electron volts times 5,600, we can say that's a little bit less than 20,000 electron volts in total on energy, or it's less than 20 kiloelectron volts. Or in other words, this is less than a seventh, or in other words, it's less than 120 electron volts per kiloelectron volt. So we're having here a conversion of the original energy into visible light, the energy we have in the visible light, of around 12%.